Before life, before oceans, before continents, before the sky turned blue, there was Earth, not the Earth we know, but a planet locked in fire, darkness, and violence. A world that existed for hundreds of millions of years without a single living thing. No forests, no animals, no microbes drifting in the sea, just stone, heat, and time. This is the story of Earth before life was possible. The first billion years when the planet itself was still being built. Imagine standing on Earth. 4.5 billion years ago, there is no ground beneath your feet, only molten rock, no air to breathe, only choking gas and ash, no horizon, just glowing heat stretching endlessly in every direction. The sun hangs dimmer in the sky, wrapped in thick haze. Asteroids streak overhead like constant falling stars. This is not a cradle for life. This is a planet struggling to survive its own birth. Earth formed about 4.6 billion years ago from the leftover debris of the sun's creation. Around the newborn sun, a swirling disk of dust and rock circled endlessly. Tiny grains collided, stuck together, became pebbles, then boulders, then mountains of stone drifting through space. Over millions of years, gravity pulled these fragments together. Each collision released unimaginable heat. The growing Earth was not gently assembled, it was hammered into existence. Every impact melted rock. Every collision reshaped the surface. The young planet grew hotter and hotter and hotter, until the surface of Earth became a global ocean of magma. There were no continents, no solid crust, no oceans, just fire. Rivers of molten rock flowed across the planet. The surface glowed red and orange like the inside of a furnace. Any solid ground that formed would melt again within moments. Earth was not yet a world, it was a process. Above this molten surface, Earth's first atmosphere struggled to exist. It was nothing like the air we breathe today. There was no oxygen, no protective ozone layer, no gentle winds. Instead, the sky was filled with volcanic gases, carbon dioxide, methane, sulfur, and steam. Lightning cracked constantly through thick clouds. Acid rain fell not for hours or days, but for centuries at a time. The planet was loud, violent, unstable, and it would remain this way for an unimaginably long time. For the first several hundred million years, Earth was trapped in what scientists call the Hadean Aeon, named after Hades, the underworld. It is one of the least understood chapters in Earth's history because almost nothing from it survived. The reason is simple. Earth kept resetting itself. Asteroids and planetary fragments slammed into the planet again and again. Some impacts were small, others were cataclysmic. Each collision released more energy than every nuclear weapon humans have ever built combined. The surface melted repeatedly. The crust broke apart. Anything resembling stability vanished. If life tried to begin during this time, it would not have lasted. The planet simply wasn't ready. Then came the impact that would change Earth forever. A Mars-sized body collided with the young planet. The collision was so powerful that it tore molten rock from Earth's surface and hurled it into space. That debris eventually came together and formed the moon. The moon's birth was violent, but it brought balance. Its gravity stabilized Earth's spin. It slowed the planet's rotation. It calmed the wild wobble of Earth's axis. Without the moon, Earth might never have become stable enough for life at all, but stability would not come quickly. Not yet. For tens of millions of years after the moon formed, Earth remained hellish. The surface was still molten in many regions. Volcanoes erupted constantly. Lava poured from countless cracks in the crust. The planet radiated heat into space, slowly cooling, but never fast enough. And then the bombardment intensified. A period known as the Late Heavy Bombardment followed. Asteroids rained down on Earth relentlessly. The sky was never dark. Impacts lit the surface continuously. Entire regions were vaporized in seconds. Oceans, if they had begun to form, boiled away. The crust shattered again and again. Earth was not just being struck. It was being tested, yet something remarkable was happening beneath the chaos. Despite the violence, despite the heat, despite the endless destruction, Earth was slowly changing. Each impact added new material. Each eruption released gases. Each cooling cycle allowed tiny pieces of crust to survive a little longer than before. The planet was learning how to hold itself together. Eventually, something extraordinary occurred. The bombardment slowed, not suddenly, not dramatically, but gradually. Impacts became less frequent. The surface had time to cool just a little longer each time. For the first time, solid ground could persist. As Earth cooled, water vapor in the atmosphere began to condense. Rain fell, not gentle rain, but torrential storms that lasted thousands of years. The sky darkened, steam rose from the surface as water met hot rock. Slowly, basins filled. The first oceans formed. These early oceans were nothing like today's seas. They were hot, dark, chemically hostile. Water was acidic, loaded with dissolved minerals, stained by iron and volcanic compounds. There were no waves shaped by wind, only the restless motion of a planet still releasing heat from within. But something profound had changed. Earth now had liquid water, and water remembers. For the first time, Earth could preserve chemistry. Molecules could persist, reactions could repeat, complexity could build instead of being erased. The oceans became vast chemical laboratories. Lightning struck the surface. Hydrothermal vents poured energy into the water from below. Volcanoes continued to shape the atmosphere above. Energy was everywhere, but life was still absent. The sky remained thick and orange-gray. The sun appeared faint, filtered through dense gases. Ultraviolet radiation reached the surface unhindered. There was no oxygen to block it, no ozone shield. The surface of Earth was still deadly. If you could stand on its shores, you would not see blue water or green land. You would see dark rock meeting steaming seas under a heavy, suffocating sky. Still, the planet endured. The crust thickened in places. Early continental fragments formed, small, unstable, constantly breaking apart and reforming. Plate tectonics may have already begun, recycling the surface, dragging old rock downward, bringing new material up from below. Earth was becoming dynamic, not just violent. Time passed, not years, not centuries, hundreds of millions of years. The planet cooled further, the impacts dwindled, the oceans deepened and stabilized. Earth entered a new phase of its existence, a phase where change was no longer constant destruction but gradual transformation. And yet there was still no life, no cells, no DNA, no metabolism, just chemistry, but chemistry growing more complex with every passing million years. By the end of Earth's first billion years, the planet had finally crossed an invisible threshold. It was no longer resetting itself, it could now remember. The surface could remain intact long enough for patterns to form, for reactions to repeat, for complexity to build. Earth was still lifeless, but it was no longer uninhabitable. Gentle pause life did not appear in a flash. It waited for the planet to cool, waited for the oceans to settle, waited for the violence to fade into rhythm. The first billion years were not about life, they were about preparation. For hundreds of millions of years, Earth had existed in a state of near constant forgetting. Every surface melted, every ocean boiled away, every fragile structure erased before it could matter. But now something fundamental had changed. The violence had not vanished, but it had slowed enough for patterns to endure, for chemistry to repeat itself, and for the planet to begin holding on to its own history rather than endlessly wiping it clean. Earth had entered an age where memory became possible. The oceans, once temporary and unstable, now remained for millions of years at a time, spreading across much of the planet's surface as vast, dark expanses of water that absorbed heat, dissolved minerals, and quietly collected the chemical ingredients of the future. These early seas were warm, sometimes near boiling, and saturated with iron, sulfur, carbon compounds, and dissolved gases released continuously from the planet's interior. They were not friendly waters, they were reactive waters. Above them, the atmosphere remained thick and alien, composed almost entirely of gases that would suffocate modern life. Carbon dioxide, methane, nitrogen, ammonia swirling beneath a sun that shone weaker than it does today. Its light filtered through dense haze and volcanic clouds. There was no blue sky, no white clouds, only a heavy, copper-colored ceiling that trapped heat and scattered light, casting the world in permanent twilight. Lightning storms rolled endlessly across the planet, cracking through the atmosphere and striking the ocean surface with immense energy, while beneath the waves, deep fractures in the crust released superheated water rich with minerals, forming hydrothermal vents that glowed faintly in the darkness. Energy flowed everywhere, from above, from below, from within, and energy is what chemistry needs. In these oceans, molecules collided. Simple compounds formed more complex ones. Carbon bonded with hydrogen, oxygen, nitrogen, and sulfur, assembling chains, rings, and structures that had never existed before on this planet. Most reactions failed. Most structures broke apart as quickly as they formed, but some endured not because they were alive, but because they were stable enough to survive the conditions around them. This was not life, not yet, but it was no longer random. The oceans were becoming selective. In shallow waters near volcanic shores, cycles began to repeat. Day after day, heat rose and fell. Water evaporated, then returned as rain. Pools concentrated chemicals, dried partially, then refilled, allowing reactions to proceed step by step instead of all at once. Each cycle added complexity, testing countless molecular arrangements over millions of years. Elsewhere, deep beneath the surface, hydrothermal vents provided something equally important: consistency. Unlike the chaotic surface, these environments remained relatively stable, protected from ultraviolet radiation and violent temperature swings, offering continuous sources of heat and chemical gradients that encouraged molecules to organize rather than scatter. Some scientists believe these dark, mineral-rich environments may have been where the most important steps occurred, not suddenly, not dramatically, but slowly, patiently, over time scales almost impossible to comprehend. Still, Earth remained lifeless. There were no cells drifting in the water, no metabolism converting energy into growth, no reproduction. The planet was experimenting endlessly without yet crossing the boundary into biology. What makes this period so extraordinary is not what existed, but what did not. There was still no oxygen. If you could somehow breathe this air, your lungs would burn within seconds. The oceans, deprived of oxygen, were dark and heavy with dissolved metals, especially iron, which remained suspended rather than rusting and sinking as it would today. The world was chemically reduced, not oxidized, a state utterly foreign to modern Earth. And yet this oxygen-free world was not a failure. It was a requirement. Life, when it finally appeared, would depend on this very absence. As millions of years passed, Earth's crust thickened further, stabilizing enough for early continental fragments to survive longer, colliding, merging, and breaking apart in slow motion across the surface of the planet. Plate tectonics, still poorly understood in this era, may already have been operating, recycling material between the surface and the mantle, ensuring that nutrients flowed into the oceans and that the planet never became geologically stagnant. Earth was alive with motion, just not biological life. The planet's interior continued to cool, but it remained active enough to drive volcanoes, earthquakes, and chemical exchange, maintaining a delicate balance between stability and change. Too much stability and chemistry would stagnate, too much chaos and complexity would never last. Earth hovered between the two. This balance is easy to overlook today, standing on a world that feels permanent and calm, but during this time nothing about Earth was guaranteed. The oceans could still boil away if volcanism surged. The atmosphere could still thicken or thin dramatically. A single large impact could still alter the planet's trajectory. Life, when it arrived, would do so on borrowed time, yet something remarkable was happening at scales too small to see. Molecules were beginning to interact in ways that hinted at purpose, not intention, but persistence. Some chemical structures helped others form. Some reactions produced environments that favored their own continuation. Feedback loops emerged, chemistry influencing chemistry. The line between non-living and living matter grew thinner. Earth had become a planet of potential, not because it was gentle, but because it was consistent. By the end of this period, near the close of Earth's first billion years, the planet had settled into a new identity. It was no longer a molten world, no longer endlessly erased, no longer purely hostile to complexity, but it was still silent, no heartbeat, no breath, no life, and yet everything necessary was now in place. Water that endured, energy that flowed, chemistry that repeated, time that stretched endlessly forward. The stage was set. Life did not need miracles. It did not need perfection. It only needed a planet that could finally stop forgetting long enough for something fragile to persist. Earth had become that planet. For most of Earth's existence up to this point, nothing on the planet could be said to want anything. Rocks did not seek to grow. Oceans did not strive to change. Molecules drifted, collided, reacted, and disappeared without memory or intention. The planet moved endlessly, but nothing on it endured with purpose. And yet within this restless world, chemistry had begun to behave in ways that were no longer entirely random. Deep within the oceans, and along the boundaries where water met rock and heat rose from the planet's interior, certain molecular arrangements proved more durable than others, persisting not because they were alive, but because the environment quietly favored their continued existence. Carbon-based molecules, flexible and capable of forming long chains, assembled and reassembled over unimaginable spans of time, occasionally producing structures complex enough to interact with their surroundings in subtle but important ways. Some absorbed energy more efficiently, some stabilized nearby reactions, some encouraged the formation of similar molecules. None of this was life, but it was no longer chaos. In the warm, mineral-rich waters of early Earth, chemistry began to explore possibility space, testing combinations, repeating reactions, and slowly, almost imperceptibly, discovering pathways that led toward greater complexity rather than immediate collapse. This was not guided. There was no plan. Only time, vast, patient, unending time, allowing improbable events to eventually occur simply because everything else had already been tried. Among the countless molecular experiments taking place across the planet, one challenge stood above all others. How could information persist? Without memory, complexity cannot accumulate. A structure that forms once and disappears leaves no trace, but a structure that can copy itself, even imperfectly, introduces something entirely new into the universe: continuity. Somewhere in Earth's ancient oceans, perhaps near sunlit shores or perhaps in the darkness of hydrothermal vents, molecules capable of storing and transferring chemical information began to appear. Not DNA as we know it today, not even RNA in its modern form, but simpler precursors, molecules that could both hold information and participate directly in chemical reactions, allowing them to influence their own replication. This was the quiet revolution, no explosion. No dramatic transformation of the planet, just molecules that lasted a little longer than others and occasionally produced copies of themselves before breaking apart. Replication did not need to be perfect. In fact, imperfection was essential. Each copy differed slightly from the original, and those differences determined whether the new molecule persisted or vanished under the conditions around it. Some copies failed immediately, others endured, a few performed better than their predecessors. For the first time in Earth's history, selection had entered the picture. Not biological natural selection, not yet, but chemical selection, where stability and replication determined which structures became common and which faded into obscurity. The planet itself became the judge. The oceans, vast and interconnected, allowed successful molecular systems to spread, while unsuccessful ones disappeared without record. Energy continued to flow through lightning, heat, and chemical gradients, powering reactions that would have been impossible in a colder, quieter world. Earth was not merely hosting chemistry, it was shaping it. One of the greatest challenges these early molecular systems faced was isolation. In the open ocean, reactions dispersed too easily. Molecules drifted apart, diluted beyond usefulness, or destroyed by radiation and heat. To progress further, chemistry needed boundaries. Those boundaries may have arrived in the form of simple membranes, thin, flexible barriers made from lipid-like molecules that naturally assembled in water, forming tiny bubbles that separated an interior chemical environment from the surrounding ocean. These structures did not need to be alive to be revolutionary. They concentrated chemistry. They protected reactions. They allowed internal processes to differ from the outside world. Inside these primitive compartments, molecular systems gained something unprecedented: privacy. Within these boundaries, replication could occur more reliably. Reactions could proceed in sequences rather than chaos. Chemical gradients could be maintained, allowing energy to flow from one process into another. The distinction between inside and outside, so fundamental to life, had begun to emerge. Still, these systems were fragile. They did not grow in any meaningful sense. They did not adapt with intention. They did not evolve rapidly. Most failed, but a few persisted, and persistence over time changes everything. Earth did not notice this transition. The oceans did not change color. The sky did not shift. The planet looked exactly as it had before, yet something irreversible had begun. Once information can copy itself, the future is no longer constrained by the present. Small advantages accumulate, complexity builds. And the pace of change, once glacial, begins to accelerate. These early replicating systems did not breathe, they did not feed, they did not think, but they interacted with energy in ways that allowed them to continue existing, drawing from chemical gradients and releasing waste back into the environment. They were not organisms, but they were no longer just chemistry. Over time, over hundreds of millions of years, these systems became more efficient. Replication improved, boundaries stabilized. Interactions between molecules became coordinated rather than accidental. Chemical networks emerged where one reaction fed another in repeating cycles. At some point, impossible to pinpoint, the line was crossed. The planet had produced its first life, not suddenly, not dramatically, but quietly. There was no single moment when Earth went from lifeless to alive, no dividing line etched into stone. Only a gradual transition where chemistry behaved increasingly like biology until the distinction became meaningless. These earliest life forms were simple beyond modern comprehension. Single-celled, anaerobic, dependent entirely on their environment. They did not produce oxygen. They did not reshape the planet. They existed in small numbers, clinging to niches where energy and chemistry aligned just right. Yet even in their simplicity, they carried something extraordinary. They could change. Variation appeared naturally as replication continued. Some systems were slightly better at maintaining their boundaries. Others processed energy more efficiently. Some survived conditions that destroyed their neighbors. Selection intensified. Evolution had begun. For the first time, Earth was no longer changing alone. Life had joined the process. The planet was still hostile. Ultraviolet radiation bombarded the surface. Volcanoes continued to erupt. Asteroid impacts still occurred. But life persisted, not everywhere, not abundantly, but stubbornly. Each generation carried the accumulated successes of the past. Each failure refined what came next. Earth had crossed a threshold from which there would be no return. Even if life vanished entirely, the possibility had been proven. The planet was capable, and yet at this stage life was still a whisper, invisible, insignificant by planetary standards. The world remained dominated by rock, water, and sky. Life was merely learning to exist. For a long time after life first appeared, Earth gave no obvious sign that anything had changed. The oceans remained dark and heavy with dissolved metals. The skies stayed thick and colorless, filtering sunlight through haze. Volcanoes continued to erupt, and the surface of the planet still bore the scars of its violent youth. Life did not announce itself, it simply endured. The earliest living systems on Earth were unimaginably small, fragile, and simple, existing as microscopic entities suspended in water or clinging to mineral surfaces where chemistry and energy aligned just well enough to sustain them. They did not swim, they did not hunt, they did not compete in any recognizable way. They merely existed, converting energy, repairing themselves, and reproducing slowly, generation after generation, in environments that could still erase them at any moment. These first life forms lived in a world without oxygen, and for them, oxygen would have been poison. Their metabolisms relied on chemical reactions that modern life rarely uses, drawing energy from sulfur compounds, iron, hydrogen, and other substances abundant in the early oceans. They were perfectly adapted to a planet that modern organisms would find lethal. Life did not spread evenly across Earth. It clustered in warm, shallow waters near volcanic islands and coastlines where sunlight penetrated and chemical nutrients flowed freely. Life found opportunity. In the deep ocean near hydrothermal vents, life found stability, protected from radiation and temperature extremes. Between these regions lay vast stretches of ocean where life may have struggled to gain a foothold at all. Each environment favored different strategies. Some organisms relied on heat-driven chemistry. Others used mineral gradients. A few began to harness sunlight, not yet producing oxygen, but capturing energy in simpler ways that allowed them to persist where chemical fuel was scarce. Life diversified quietly. Yet even as life multiplied, it remained a minor presence on the planet. For hundreds of millions of years, biology did not dominate Earth. Geology did. The planet's interior still controlled the surface, driving cycles of volcanism, tectonic motion, and chemical exchange that shaped oceans and atmosphere alike. Life adapted to Earth. Earth did not yet adapt to life. One of the most profound changes brought by early life was invisible. Life altered chemistry not through force, but through repetition. Every metabolic reaction released waste. Every generation altered its surroundings slightly. Over immense spans of time, these small changes accumulated. Iron dissolved in the oceans reacted with biological byproducts. Sulfur cycles intensified. Carbon moved through new pathways. The oceans became chemically layered with different conditions at different depths, shaped not only by physics and geology, but by the presence of living systems processing energy in new ways. Still, the sky remained unchanged. No oxygen accumulated. No protective ozone layer formed. Ultraviolet radiation continued to penetrate the surface waters, limiting where life could safely exist. The planet remained harsh, but life was learning how to survive within it. One of the defining features of this early biosphere was its slowness. Evolution proceeded, but at a pace measured in tens of millions of years. Mutations accumulated gradually. Adaptations spread slowly. There were no sudden leaps, no explosions of complexity. Life remained microbial, simple, and largely invisible, and yet beneath this simplicity lay an extraordinary resilience. When environments shifted, life retreated rather than vanished. When temperatures rose, organisms migrated deeper. When chemistry changed, metabolisms adapted. Life did not conquer Earth, it endured Earth. At times, conditions worsened dramatically. Volcanic activity surged, releasing vast amounts of gases that altered ocean chemistry and climate. Large impacts still occurred occasionally, disrupting ecosystems and heating the surface. Entire regions may have been sterilized repeatedly, but life returned again and again. Each recovery strengthened the biosphere. Each bottleneck refined survival strategies. Life became harder to erase. Somewhere during this long microbial age, a transformative innovation emerged, not suddenly, not universally, but in isolated pockets where conditions allowed. A new way of capturing energy. A way that used sunlight more efficiently than any chemical reaction before it. Photosynthesis had begun. At first, this process did not involve oxygen. Early photosynthetic organisms used alternative chemical pathways, capturing light energy without splitting water or releasing oxygen into the environment. This innovation allowed life to expand into regions where chemical fuel was scarce but sunlight was abundant. Shallow waters became more biologically active. Life crept closer to the surface. Sunlight, once a threat, became a resource. The balance began to shift. These early photosynthetic systems did not immediately transform the planet. They were limited in scope, vulnerable to radiation, confined to niches where conditions remained stable, but they represented a new relationship between life and Earth. For the first time, biology was tapping directly into the largest energy source available to the planet. Still, oxygen remained absent. The world was not yet ready. Life continued to diversify in subtle ways. Cell membranes became more complex, metabolic networks grew more interconnected, replication became more reliable, genetic information was stored, copied, and modified with increasing precision. Evolution accelerated not dramatically but steadily. By now, life had existed on Earth for hundreds of millions of years, yet if viewed from space, the planet would still appear lifeless, dark oceans. Muted continents, a hazy alien atmosphere, no signature of biology detectable from afar. This long invisibility is one of the most humbling aspects of Earth's history. Life does not require dominance to persist. It does not need to reshape the planet immediately. For most of its existence, life survived quietly unnoticed, content to exist within narrow margins. But this quiet persistence was laying the groundwork for something far more dramatic. A transformation so profound that it would alter the chemistry of the oceans, the composition of the atmosphere, and the trajectory of evolution itself. Life was preparing to change the sky. That change would take time, hundreds of millions of years, but it would begin with a simple innovation, the ability to split water molecules using sunlight, releasing oxygen as waste. an act that would poison most existing life, an act that would nearly destroy the biosphere, an act that would ultimately make complex life possible. Earth was approaching one of the most dangerous moments in its history, a moment when life's greatest innovation would become its greatest threat. For most of its early history, Earth's sky had never changed. It had thickened and thinned, darkened and lightened, filled with volcanic gases and dust. But its chemistry remained fundamentally the same, hostile to oxygen, indifferent to life, and utterly unlike the atmosphere we know today. Then quietly, without intention or awareness, life began to alter it. The organisms responsible did not plan to transform the planet. They did not evolve with the future in mind. They simply discovered a new way to survive. Somewhere in Earth's shallow waters, a lineage of simple microbes learned how to use sunlight in a more powerful way than ever before. Instead of relying on scarce chemical fuels, they learned to draw energy directly from the sun by splitting water molecules apart. This process released a waste product, oxygen. At first, that oxygen did not enter the air. The planet was full of things eager to absorb it. Iron dissolved in the oceans reacted immediately, forming rust-like compounds that sank to the seafloor. Volcanic gases neutralized it. Surface minerals bound it. For millions of years, oxygen never accumulated. It was produced and instantly consumed. The oceans slowly changed color as iron fell out of solution, forming vast layered deposits that still mark this transition in Earth's rock record today. These banded formations are silent witnesses to a world undergoing chemical upheaval, a planet struggling to absorb something entirely new. Life continued producing oxygen, unaware that it was slowly overwhelming the planet's ability to contain it. Each generation added a little more. Each shallow sea became slightly more reactive. Each mineral sink filled one by one. Eventually, the balance tipped. The oceans could no longer absorb all the oxygen being produced. For the first time in Earth's history, oxygen began to leak into the atmosphere. The change was subtle at first, barely detectable, but it was irreversible. Oxygen is an aggressive molecule. It reacts violently with many substances. To early life, it was lethal. The very gas that would one day make animals possible was, at first, a planetary poison. As oxygen levels rose, entire ecosystems collapsed. Anaerobic organisms, adapted to oxygen-free environments, found themselves surrounded by a toxin they could not tolerate. Some retreated to deeper waters, others burrowed into sediments. Many died. This was Earth's first mass extinction, and it was caused by life itself. The planet entered a long, unstable period known as the Great Oxidation Event, a transformation that unfolded over hundreds of millions of years rather than in a single catastrophic moment. Oxygen levels fluctuated, climate shifted, chemistry changed everywhere at once. One of the most dramatic consequences was the cooling of the planet. Methane, a powerful greenhouse gas that had helped keep early Earth warm under a faint sun, reacted with oxygen and disappeared from the atmosphere. With less heat trapped, global temperatures dropped, ice spread. Earth may have frozen almost entirely, entering a series of global or near-global ice ages that pushed life to the brink. The planet that life had slowly stabilized was suddenly hostile again, but life endured. Some organisms adapted to oxygen, turning a deadly molecule into an opportunity. Oxygen allowed for far more efficient energy extraction than any previous metabolic pathway. Cells that could tolerate it and eventually use it gained enormous advantages. They grew faster, processed energy more efficiently, supported greater complexity. These adaptations did not happen quickly. Oxygen resistance evolved slowly, unevenly, and painfully. For millions of years, the biosphere remained fractured, divided between oxygen-poor refuges and newly oxygenated environments where only a few survivors could persist. Meanwhile, the atmosphere continued its transformation. As oxygen accumulated, it formed an ozone layer high above the surface, blocking harmful ultraviolet radiation for the first time. The surface of Earth became safer. The oceans became more hospitable near the surface. Life expanded upward, outward, and into new niches. The sky itself began to change color. With less haze and more oxygen and nitrogen, light scattered differently. Earth's sky gradually turned blue. This was not merely a visual change, it was a signal. The planet had crossed another threshold. Oxygen altered the chemistry of every environment it touched. Rocks weathered differently, oceans layered more distinctly, nutrients cycled in new ways, Earth became more dynamic, more complex, more interconnected. Life, once a minor passenger on a hostile world, had become a planetary force. And yet, despite this transformation, complex life still did not exist. There were no plants, no animals, no multicellular organisms as we recognize them. The planet was still dominated by microbes, but those microbes now lived in a world rich with possibility. Energy was abundant, the environment was more stable, the atmosphere protected the surface rather than destroying it. Evolution accelerated. The groundwork had been laid for the next great transition, the rise of complexity. Cells would begin cooperating. Specialization would emerge. Life would learn to build bodies rather than merely survive as individuals. But that story lies beyond the first billion years, beyond the silent preparation, beyond the long struggle to make Earth habitable. The world we recognize today, green, alive, breathing, is the product of these ancient, invisible revolutions. A planet shaped not by intention but by persistence, not by design but by time. Earth did not begin as a home for life, it became one, slowly, reluctantly. Tremendous cost. After oxygen entered the atmosphere, Earth did not suddenly become a paradise for life. The transformation of the planet was slow, uneven, and often brutal, unfolding across spans of time so vast that progress was nearly invisible to anything living through it. For millions of years, the biosphere remained dominated by simple organisms, adapting cautiously to a world that was still unstable, still changing, and still capable of erasing entire ecosystems without warning. Oxygen had altered the rules, but it had not yet rewritten the outcome. In many ways, the presence of oxygen made survival harder before it made survival easier. The same molecule that allowed cells to extract far more energy also damaged proteins, shredded genetic material, and disrupted ancient metabolic pathways that had evolved in its absence. Life was forced to reinvent itself, slowly, painfully. Some organisms retreated permanently into oxygen-free environments, finding refuge deep in sediments, beneath the ocean floor, or within chemically isolated pockets where the new atmosphere could not reach. Others adapted, developing molecular defenses that neutralized oxygen's destructive effects, transforming a deadly gas into a usable tool. This division would persist forever. Even today, Earth hosts both oxygen-breathing life and organisms that cannot tolerate oxygen at all. The biosphere became layered. Surface waters grew more oxygen-rich, while deeper regions remained anoxic. Shallow environments favored new metabolic strategies. Deep environments preserved ancient ones. Life diversified not through dominance, but through separation. As cells adapted to oxygen, they gained access to far greater energy yields than had ever been possible before. With more energy available, cells could afford inefficiency. They could afford redundancy. They could afford complexity. This surplus changed everything. Over time, cells began experimenting with internal organization. Structures formed within them, membranes, compartments, specialized regions, allowing different chemical processes to occur simultaneously without interference. This internal complexity did not appear all at once. It accumulated gradually, piece by piece, refinement upon refinement. Some cells developed the ability to engulf others without digesting them. These internal partners provided useful functions, processing energy, breaking down waste, or performing specialized chemical reactions. In exchange, they received protection and resources. What began as cooperation eventually became integration. This was one of the most important transitions in the history of life. Cells within cells, partnerships becoming permanence, complexity becoming identity. The descendants of these merged systems would one day form the foundation of plants, animals, fungi, and countless other organisms. But for now, they remained rare, fragile, slow-growing. Earth's environment still imposed strict limits. Oxygen levels fluctuated, climate shifted repeatedly, ice advanced and retreated. The planet oscillated between warmth and cold, stability and disruption. Each shift tested life's ability to adapt. Complex cells, though powerful, were also vulnerable. They required stable conditions, reliable energy sources, protection from extreme stress. For a long time, these conditions were scarce. As a result, complexity evolved in fits and starts, appearing, disappearing, reappearing. The planet experimented repeatedly, refining the idea of complexity until it could endure. Meanwhile, microbial life continued to dominate. Vast mats of microorganisms spread across shallow seas, processing nutrients, cycling carbon, and quietly shaping the chemistry of the oceans and atmosphere. These communities stabilized environments, dampening extremes and creating pockets of relative consistency. Life was learning how to engineer its surroundings. This was not conscious, not intentional, but the effect was profound. Life no longer merely responded to Earth, it began to modify it. Over hundreds of millions of years, the atmosphere became increasingly oxygen-rich, though still far below modern levels. The ozone layer strengthened, ultraviolet radiation decreased, surface environments became safer, opportunities expanded. With fewer environmental barriers, life began exploring new strategies. Cells formed loose associations, groups cooperated temporarily. Division of labor emerged in primitive forms. Some cells specialized in energy production, others in protection, others in reproduction. These early collaborations were unstable. They broke apart easily. They lacked coordination, but they represented a new direction. Life was learning that survival could be shared. Time continued its relentless march. Generations passed. Adaptations accumulated. The biosphere grew more complex, more resilient, and more interconnected. The pace of evolutionary change, once glacial, began to quicken. Earth itself had changed. The planet was no longer dominated by chaos. Not peaceful, not gentle, but predictable enough for complex systems to endure. What is most striking about this period is how long it took. From the first appearance of life to the rise of true complexity, billions of years passed. Life waited, experimented, failed, tried again. This patience is written into the fabric of biology. Complexity is not rushed, it is earned through endurance. By the end of this long transition, Earth was poised on the edge of another threshold. Life had mastered energy. Learned cooperation. It had learned resilience. All that remained was scale. In the future, life would grow larger, more organized, more visible. But that future depended entirely on the quiet victories of this forgotten era. An era without animals, without plants, without spectacle. The first billion years of Earth were not a prologue. They were the foundation. Every forest, every animal, every human thought traces its lineage back through this deep, silent past. Earth did not rush toward life. Life did not rush toward complexity. Together, they learned patience. By the time Earth had settled into this long age of microbial dominance, the planet had reached a kind of uneasy equilibrium, not calm, not gentle, but no longer violently self-destructive, and no longer erasing its own surface with relentless regularity. The crust persisted, the oceans remained, the atmosphere, though still foreign, now followed patterns rather than chaos. And life, fragile as it remained, had learned how to survive within narrow margins instead of being erased entirely. What is difficult to grasp from a modern perspective is just how empty this world would still appear. For more than 1 billion years after life first emerged, Earth had no forests, no animals, no movement visible from afar, and no sound other than wind, water, and the slow rumble of geology. Life was everywhere, and yet nowhere to be seen. If you could drift above the planet at this time, the oceans would stretch endlessly below you, dark and heavy, occasionally broken by small island chains formed by volcanic activity, their surfaces bare, black, and lifeless to the eye. The continents, still small and fragmented, would appear as scars of stone rising from the sea, shaped by erosion but untouched by roots or soil. There would be no green, no color signaling abundance. No sign that biology had already rewritten the chemistry of the world. And yet beneath the surface, Earth was alive with activity. Microbial communities spread across shallow seafloors, forming layered mats that trapped sediment, stabilized coastlines, and processed nutrients in slow, deliberate cycles. These structures, fragile, flat, and easily destroyed, were among the earliest ecosystems the planet ever hosted. They did not compete. They endured. Within these communities, countless species of microorganisms interacted in ways that were neither cooperative nor hostile in any familiar sense. Some produced waste that others consumed. Some altered their surroundings in ways that benefited neighbors unintentionally. Some simply survived in the spaces left behind. Life was not yet a struggle for dominance. It was a negotiation with environment. Time, once again, is the central character. Thousands of generations passed without visible change. Millions of years produced only subtle refinements. Evolution was not dramatic, it was patient. Earth itself continued to shape the biosphere through cycles that operated far beyond the scale of any living organism. Volcanoes injected gases into the atmosphere, warming the planet, only for weathering processes to slowly draw those gases back into the oceans and rocks, cooling it again. Ice advanced and retreated across high latitudes. Sea levels rose and fell. The planet breathed slowly. Each cycle tested life's flexibility. Some lineages vanished, others adapted, but extinction was not yet the defining force it would later become. Life remained simple enough that loss was often temporary, and recovery, though slow, was almost inevitable. One of the most important developments during this long era was the gradual tightening of biological feedback loops. Life began influencing Earth in ways that made environments more stable rather than less. Microbial mats slowed erosion. Biological activity altered mineral formation. Chemical cycles became more regulated as life processed carbon, sulfur, and nitrogen with increasing efficiency. The planet was becoming less extreme, not because Earth intended to be habitable, but because life dampened volatility simply by existing. This stabilization created windows of opportunity, longer periods without catastrophe, more consistent temperatures, oceans that remained chemically similar over extended spans of time. These windows were still narrow, but they were wide enough for complexity to occasionally persist rather than collapse. Within these windows, cells experimented. Genetic material accumulated refinements, regulatory mechanisms emerged, reactions that were once loosely connected became coordinated, biological systems gained internal rhythm. Yet even now, progress was fragile. Complex cells were still rare. Multicellular cooperation remained unstable. Most experiments failed. The planet was unforgiving of inefficiency. What makes this period so humbling is how often life came close to stagnation. There were long stretches when little seemed to change at all. No obvious increases in size, no leaps in diversity, just persistence. But persistence is not inactivity. Every generation carried slight differences. Every survival event selected for subtle advantages. Over time, these microscopic changes accumulated into transformations that could not be reversed. Earth's oxygen levels continued to rise, though unevenly, creating gradients across the planet. Some environments became rich in oxygen, others remained anoxic. Life adapted to this patchwork world, specializing in different conditions rather than converging on a single strategy. Diversity increased quietly. With more oxygen available, energy budgets expanded. Cells could maintain larger genomes. They could afford more regulatory complexity. They could support internal structures that would have been energetically impossible in earlier eras. At the same time, oxygen forced life to evolve safeguards. Antioxidant systems developed. DNA repair mechanisms improved. Cells became better at maintaining internal stability in the face of chemical stress. These innovations did not attract attention, but they would become essential for everything that followed. One of the most subtle yet profound shifts during this era was the increasing separation between biological time and geological time. Early life had been almost entirely at the mercy of planetary processes. As biology became more robust, it gained the ability to buffer itself against environmental swings. Life still depended on Earth, but it was no longer completely dominated by it. This growing independence allowed evolutionary experimentation to persist long enough for complexity to stabilize. Temporary successes became lasting lineages. Failures still occurred, but not everything reset to zero. The oceans, now chemically layered and biologically active, became cradles of innovation. In shallow waters, sunlight powered new metabolic pathways. In deeper regions, chemical energy continued to sustain ancient lineages. The biosphere became vertically structured. These layered environments encouraged specialization. Different depths favored different strategies, different temperatures selected for different adaptations. Life diversified not by spreading everywhere but by partitioning space. Over time, interactions between organisms grew more intricate. Some microbes produced compounds that inhibited competitors. Others evolved resistance. Chemical signaling emerged primitive communication without intention or awareness. Life was beginning to influence life. This interaction drove further complexity. Organisms no longer evolved solely in response to the environment. They evolved in response to each other. Evolution accelerated. Still, Earth remained quiet. No sounds, no movement visible to the naked eye, just water, stone, and sky. If a conscious observer could have watched this planet across hundreds of millions of years, they might have concluded that nothing important was happening. That life had stalled. That Earth had reached a dead end. They would have been wrong because beneath the stillness, systems were aligning. Energy, chemistry, stability, and time were converging towards something that had never existed before. Not suddenly, not inevitably, but increasingly possible. The planet had learned restraint. Life had learned endurance. Together they were approaching a moment where size, structure, and cooperation could persist rather than collapse. Yet this moment did not arrive easily. There were setbacks, climate disruptions, periods of reduced oxygen, times when ice advanced far toward the equator, constricting habitable zones and pushing life into refuges. These events tested the resilience of emerging complexity. Each time, life survived, diminished, simplified, but not erased. Each recovery built upon what remained. This cycle of stress and survival shaped biology profoundly. Life became conservative, redundant, resilient. Traits that favored survival over speed were preserved. These traits would later enable rapid expansion when conditions allowed. By now, Earth was no longer merely hosting life, it was co-evolving with it. The planet's chemistry reflected biological activity. The biosphere reflected planetary constraints. Neither could be understood without the other. This long era of quiet development laid the foundation for visibility, for size, for movement. But those features were still far in the future. For now, Earth remained a world of whispers. A world where the most important events occurred at scales too small to see, across times too long to feel, driven by processes too subtle to notice in a single lifetime. And yet everything familiar traces back to this silence. Every tree, every animal, every human breath. All of it rests on the patience of a planet that took more than 1 billion years just to learn how not to destroy what it created. We will pause here, not at an ending, but at a moment of suspension. A world alive, yet still restrained, complexity present, yet cautious. A planet on the verge of becoming something entirely different, but not yet ready to reveal it. As Earth moved deeper into this long, restrained phase of its history, time itself seemed to stretch, not because events slowed, but because change had learned how to move in subtler ways, shaping the planet not through sudden upheaval, but through accumulation so gradual that its effects were nearly invisible until they could no longer be ignored. The world no longer burned with the chaos of its birth, yet it was far from peaceful, existing instead in a state of constant adjustment, where forces rose and fell, climates shifted, and chemistry flowed through cycles that repeated endlessly, refining both the planet and the life it carried. The oceans remain the dominant feature of Earth's surface, vast and ancient, covering most of the planet and acting as both shield and crucible, buffering life from extremes while simultaneously exposing it to slow, relentless pressure to adapt. Within these waters, life continued its quiet expansion, not outward in dramatic bursts, but inward, deepening its complexity one adjustment at a time, refining the systems that allowed it to endure rather than simply survive. The earliest microbial ecosystems, once scattered and fragile, now formed more persistent networks, spreading across continental shelves and shallow basins where sunlight, nutrients, and relative stability overlapped for long enough to allow communities to mature rather than collapse. These ecosystems did not behave as individual organisms, but as collective systems, where the success of one depended on the byproducts of another, and where survival was less about competition and more about balance within narrow chemical margins. Energy moved through these systems slowly, captured, transformed, released, and reused, cycling endlessly through processes that grew more efficient with each passing million years, not because life sought efficiency, but because inefficiency simply did not last. The surface of the planet still bore no vegetation, no roots to break rock into soil, no organic layers to soften the land, and so erosion remained a purely physical process, driven by water, wind, and gravity rather than biology. Rivers carved stone directly, waves struck bare rock, sediment flowed freely into the oceans, feeding microbial communities that depended on mineral nutrients rather than organic matter. Without plants to regulate atmospheric gases, Earth's climate remained sensitive, responding strongly to changes in volcanic activity, orbital variations, and the slow rearrangement of continents, which altered ocean currents and weather patterns across geological timescales. Life endured these changes not by stabilizing the planet outright, but by adapting continuously, reshaping itself to fit shifting conditions rather than attempting to impose control. The continents themselves were still assembling and reassembling, fragments drifting across the planet's surface, colliding, merging, and breaking apart in cycles that spanned hundreds of millions of years, creating new coastlines, shallow seas, and isolated basins that served as laboratories for biological experimentation. Each new configuration altered the flow of nutrients, changed the distribution of habitats, and opened opportunities for life to diversify within constraints imposed by chemistry and physics. Isolation became one of the most powerful drivers of change. When populations were separated by distance, depth, or chemistry, they diverged slowly, adapting to local conditions in ways that accumulated into meaningful differences over immense spans of time. Diversity increased, not explosively but steadily, as life explored the available space of possibility. Yet even as diversity grew, simplicity remained dominant. Most life on Earth was still single-celled, microscopic, and slow-growing, existing at scales that would be imperceptible without magnification, and living lives measured not in moments or days, but in cycles of division that occurred only when conditions allowed. The pace of existence itself was shaped by the environment. Energy was abundant in some places, scarce in others. Growth was possible at times, suspended at others. Life learned patience because patience was rewarded. One of the defining features of this era was the gradual refinement of genetic systems. As replication became more accurate, error correction mechanisms improved, and information storage grew more stable, allowing adaptations to persist rather than vanish with each generation. This stability did not eliminate variation, it preserved it. Differences could accumulate without destroying the system that carried them. Over time, genomes expanded, encoding more instructions, more regulatory controls, more ways to respond to the environment without catastrophic failure. This expansion laid the groundwork for future complexity, even though its immediate effects were subtle. At the same time, biological systems became more interconnected internally, linking reactions into networks rather than isolated pathways, allowing cells to respond to change with flexibility rather than fragility. This integration did not produce speed, it produced resilience. The planet continued to test this resilience relentlessly. Periods of warming increased metabolic rates, favoring some lineages while stressing others. Cooling periods slowed reactions, selecting for efficiency and endurance. Chemical shifts altered nutrient availability, forcing life to innovate or retreat. None of these challenges were fatal to life as a whole. They were refining pressures, shaping a biosphere that could absorb shock without collapsing entirely. The oceans, once chemically uniform in their hostility, now displayed gradients that reflected both physical processes and biological activity, with oxygen-rich surface layers above oxygen-poor depths and distinct chemical zones shaped by circulation patterns and microbial metabolism. These gradients created opportunities for specialization, allowing different life strategies to coexist without direct competition. In these layered environments, life learned to exploit boundaries. Interfaces between oxygenated and anoxic waters, transitions between light and darkness, zones where nutrients concentrated, edges became opportunities. Over time, interactions between organisms grew more complex as chemical signaling, inhibition, and cooperation emerged as natural consequences of proximity and persistence. Life was no longer evolving solely in response to its environment, it was evolving in response to itself. This shift accelerated evolutionary dynamics, even as the visible world remained unchanged. Biology gained momentum beneath the surface, building potential that would later be released in more dramatic forms. Earth's atmosphere continued its slow transformation, becoming clearer as oxygen increased and haze diminished, allowing more sunlight to reach the surface, further altering energy flows and expanding habitable zones. Yet oxygen levels still fluctuated and the biosphere remained constrained, unable to support large, energy-demanding organisms for extended periods. Complex cells, though increasingly capable, remained limited by the environment's unpredictability. They could survive, they could adapt, but they could not yet flourish at scale. This limitation imposed discipline. Complexity was tempered by necessity. Systems evolved conservatively, favoring reliability over ambition. Traits that minimized risk persisted. Time continued its quiet work. Millions of years passed with no visible landmarks, no events that would later be named, just steady accumulation. If history is often remembered for moments of sudden change, this era challenges that perspective, revealing how profoundly important long periods of apparent stillness can be. Without spectacle, without drama, without witnesses. Earth was becoming something new, not through revolution, but through endurance. Life was preparing itself, not consciously, but inevitably, for conditions that would one day allow it to expand beyond the microscopic and reshape the surface of the planet. But that expansion still lay ahead. For now, the world remained subdued, its most important processes hidden beneath water and time. The silence persisted, not empty, not meaningless, but full of preparation. And so Earth continued, turning beneath a slowly brightening sun, carrying life quietly forward, deeper into complexity, without haste, without promise, and without pause. As Earth continued along this long, restrained path, the most striking feature of the planet was not what was happening, but how little seemed to change on the surface despite the immense activity unfolding beneath it. The oceans remained dark and expansive, absorbing sunlight, heat, and minerals with equal indifference, while the continents drifted slowly, reshaping coastlines and seafloors so gradually that no living organism could ever witness their movement in real time. To exist on this earth was to live within rhythms far slower than perception. Life, still overwhelmingly microscopic, adapted itself to these rhythms, syncing its existence to cycles that unfolded over thousands, millions, even tens of millions of years, rather than days or seasons. Growth occurred when conditions allowed, dormancy followed when they did not, persistence mattered more than speed. Many organisms spent much of their existence inactive, suspended in states of minimal metabolism, waiting patiently for chemistry to shift, for nutrients to arrive, or for temperatures to settle into ranges that allowed activity to resume. This capacity for waiting became one of life's most powerful survival strategies. Earth's environments rewarded restraint. Rapid growth was risky. Aggressive expansion invited collapse. Systems that endured were those that could pause without failing. Across the planet, microbial communities thickened and thinned in response to subtle changes in chemistry, forming patterns that repeated endlessly without ever quite becoming stable enough to fix in place. These communities were shaped not by competition in the modern sense, but by tolerance, the ability to exist alongside others without destabilizing shared environments. Waste was not discarded, it was reused. One organism's byproduct became another's resource. Nutrients cycled through ecosystems in slow loops, reinforcing connections that made communities more resilient to disruption. This interconnectedness did not arise from cooperation in any conscious sense. It emerged because isolated systems failed, only networks endured. Over immense spans of time, these networks became more elaborate, incorporating greater diversity of metabolisms, more intricate exchanges of energy and matter, and increasingly fine-tuned responses to environmental change. The biosphere grew denser without becoming more visible. Meanwhile, Earth's geology continued to reshape the stage beneath life's quiet performance. Tectonic forces lifted mountains, opened rifts, and closed seas, altering the distribution of habitats and creating new environmental gradients that life would slowly explore. Each geological change acted as both disruption and opportunity. When shallow seas formed, life expanded into sunlit waters. When seas retreated, life retreated with them, preserving itself in refuges where chemistry remained favorable. When continents collided, nutrients surged. When they separated, isolation encouraged divergence. The planet itself was not stable, but it was predictable enough. One of the most subtle shifts during this era was the gradual thickening of Earth's biosphere, not in size but in influence. Life's chemical activity began to leave clearer signatures in sediments, altering mineral formation in ways that reflected biological processes rather than purely physical ones. These changes were small, but they were cumulative. Over time, rocks themselves recorded life's presence, preserving traces of metabolic activity in layered formations that marked the slow partnership between biology and geology. The planet was beginning to archive its own transformation. The atmosphere, too, continued to evolve, its composition shifting in response to both volcanic output and biological processing, oscillating between states rather than settling into equilibrium. Oxygen levels rose and fell. Greenhouse gases fluctuated. Climate responded. Life learned to endure this variability, developing flexibility rather than specialization too narrow to survive change. Generalists persisted. Specialists survived only in protected niches. This balance shaped the future trajectory of evolution, favoring systems that could tolerate uncertainty rather than those optimized for narrow conditions. Resilience became a defining trait. As internal complexity increased, cells gained greater control over their internal environments, regulating chemistry, energy flow, and replication with increasing precision. These advances did not make life faster, they made it steadier. Errors still occurred, mutations still accumulated, but systems became better at absorbing error without collapse, allowing complexity to grow without becoming fragile. This internal regulation marked a quiet turning point. Life was no longer entirely at the mercy of external chemistry. It could maintain internal consistency even as the outside world changed. Yet this control came at a cost. Complex systems required energy. They demanded stability. They could not exist everywhere. As a result, life remained unevenly distributed, thriving in some regions while remaining sparse in others. The planet was patchy, not uniformly alive, but alive enough. The oceans continued to serve as the primary arena of biological innovation, their depth and volume providing insulation against extreme change and allowing evolutionary experiments to persist longer than they could on land. Within these waters, gradients of light, temperature, and chemistry created layered habitats that encouraged diversification without requiring large-scale dominance. Surface waters supported photosynthetic life. Deeper layers favored chemical metabolisms. Boundary zones became hotspots of activity. These layered ecosystems interacted in subtle ways, exchanging nutrients and energy through slow circulation patterns that connected distant regions of the planet over geological time. Life was not localized, it was planetary. Despite this connectivity, the biosphere remained quiet. No large bodies, no visible motion, no sounds, just chemistry and time. From a distance, Earth would still appear barren. Yet its future was already encoded in the systems quietly refining themselves beneath the surface. What makes this era difficult to appreciate is how thoroughly it contradicts human intuition. We expect progress to be visible. We expect change to be dramatic. We expect beginnings to announce themselves. Earth's did not. Life took hold without spectacle. Complexity emerged without urgency. The planet learned patience long before it learned abundance. Every adaptation during this period was tested not by immediate success, but by longevity. Traits that persisted across millions of years mattered more than those that produced rapid gains. Evolution favored durability over brilliance. This preference shaped the nature of life itself: stability before expansion, control before ambition, endurance before growth. As time continued its slow advance, the biosphere accumulated potential, storing energy, information, and complexity that would one day be released in more visible forms. But for now, restraint ruled. Earth turned beneath the sun, which continued its gradual brightening, increasing the energy available to the planet and subtly shifting the boundaries of habitability. Life adjusted, adapted, waited. Nothing forced the next transition. Nothing guaranteed it. It would occur only when enough conditions aligned at once: energy, stability, chemistry, and time, allowing complexity to persist at scales larger than ever before. That alignment had not yet arrived, but it was drawing closer. And so the planet continued, neither rushing forward nor slipping backward, carrying its quiet biosphere through another long stretch of deep time, where the most important changes remained invisible but irreversible. As Earth moved through this long era of restraint and preparation, the planet began to exhibit a kind of discipline, not imposed by intention, but enforced by consequence, where only systems capable of maintaining balance through uncertainty were allowed to persist, and where excess, instability, or haste were quietly removed by the slow, indifferent pressure of time. Life adapted to this discipline not by resisting it, but by internalizing it, shaping its structures, behaviors, and rhythms around the reality that survival did not depend on speed or dominance, but on the ability to endure long stretches of unfavorable conditions without collapsing into irreversibility. The biosphere that emerged under these constraints was conservative in its architecture, favoring systems that could pause, slow, or temporarily shut down rather than push relentlessly forward, and this trait would remain embedded in life's deepest foundations long after the planet itself had changed. Cells learned to protect their internal chemistry, isolating critical reactions from external volatility, regulating energy use carefully, and maintaining reserves that could sustain them through prolonged periods of scarcity. These adaptations did not produce visible progress; they produced persistence. Across the planet, environments continued to fluctuate, but within narrower bounds than before, as Earth's internal heat output declined gradually and surface processes became more regular, allowing climatic and chemical cycles to repeat with increasing predictability. This predictability mattered more than comfort. Life does not require favorable conditions. It requires reliable ones. Where cycles repeated, adaptation could occur. Where chaos dominated, nothing lasted. The early Earth was slowly becoming a world where repetition was possible. Within the oceans, this repetition manifested as long-standing chemical gradients that persisted across thousands of generations, allowing biological systems to tune themselves precisely to specific niches rather than constantly scrambling to survive unpredictable change. In shallow waters, sunlight drove metabolism. In deeper zones, chemical energy sustained ancient pathways. At boundaries between these realms, innovation thrived. Life learned to exploit contrast. Edges became opportunities. Transitions became resources. The biosphere did not expand evenly. It thickened where conditions allowed and thinned where they did not, producing a patchwork planet where life was abundant in some places and sparse in others, but rarely absent entirely. This unevenness encouraged diversification. Isolation created difference. Difference created resilience. Genetic systems continued to refine themselves under these pressures, evolving regulatory mechanisms that allowed organisms to respond dynamically to change rather than relying on fixed responses that could fail catastrophically. Genes were no longer just instructions, they became systems of control. This control extended to energy use, as organisms learned to allocate resources carefully, prioritizing maintenance over growth during lean periods and exploiting abundance cautiously when it appeared. Wasteful strategies disappeared, efficient ones endured. The result was a biosphere that appeared static but was internally dynamic, constantly adjusting, fine-tuning, and rebalancing itself in response to shifts so slow they were imperceptible to anything living within them. Earth became a world of long games. The absence of large organisms during this era is often misunderstood as stagnation, but in reality it reflects the immense cost of size in an unstable world. Large bodies require consistent energy, stable environments, and predictable resources. Early Earth offered none of these reliably. Smallness was an advantage. Microscopic life could exploit fleeting opportunities, retreat when conditions worsened, and recover quickly from disruption. Complexity grew inward rather than outward, expressed through regulation, specialization, and integration rather than physical expansion. Over time, interactions between organisms became more structured, as metabolic byproducts shaped local environments in ways that favored certain lineages and excluded others, creating feedback loops that stabilized ecosystems without conscious coordination. Life engineered its surroundings simply by existing within them. These engineered environments were fragile. They could collapse under stress. But when they endured, they created havens where complexity could persist longer than elsewhere. Such havens were rare, but they mattered. Geological processes continued to reshape these habitats slowly, closing some and opening others, redistributing nutrients and energy across the planet and forcing life to migrate, adapt, or retreat. Each movement left traces. Each retreat preserved potential. The long persistence of microbial mats along coastlines and shallow seas created layered records of biological activity, capturing moments of stability within an otherwise shifting world. These records would become some of the earliest direct evidence of life's endurance, preserved not as fossils of bodies, but as signatures of activity. Life was not leaving monuments, it was leaving patterns. The planet itself continued to cool, its internal heat diminishing gradually, reducing the frequency of catastrophic resurfacing events and allowing surface environments to persist longer without complete disruption. This cooling did not end volcanism. It moderated it. With moderation came opportunity. Longer-lived habitats allowed evolutionary experiments to unfold across many generations without being erased prematurely. Complexity could accumulate without constant reset. Still, the biosphere remained constrained. Oxygen levels, though present, fluctuated unpredictably. Climate remained sensitive. The planet hovered near thresholds that could push it toward global cooling or warming with relatively small changes. Life learned caution. Adaptations that demanded narrow conditions failed. Those that tolerated variability survived. This filtering shaped the nature of complexity itself, favoring robustness over specialization. Internally, cells became more compartmentalized, segregating processes to minimize interference and increase efficiency, allowing more reactions to occur simultaneously without destabilizing the whole. This internal order did not produce external complexity yet, it prepared for it. The distinction between life and environment grew more pronounced as organisms exerted greater control over their internal states, maintaining consistent conditions within even as the outside world shifted. Life became more self-contained, yet this containment was never complete. Life remained dependent on Earth's cycles, on water, on energy, on chemistry. The partnership endured. As the sun continued its slow brightening, increasing the energy reaching Earth's surface, life adapted incrementally, adjusting metabolic pathways, expanding habitable zones, and exploring new niches made possible by subtle shifts in temperature and light availability. These changes were not dramatic, they were cumulative. Over hundreds of millions of years, the biosphere became more integrated, with interactions linking distant environments through slow circulation of nutrients and genetic exchange across vast timescales. Life was not isolated, it was planetary. Despite this integration, Earth remained visually unchanged. No forests softened the land, no animals stirred the waters, no colors announced abundance. The silence persisted. Yet beneath that silence lay systems capable of transformation, waiting not for a signal, but for conditions that could sustain expansion without collapse. The threshold had not yet been crossed, but it was no longer unreachable. What emerges from this deep history is not a story of inevitability, but one of constraint. Life did not surge forward because it could. It advanced only when the planet allowed it. Every step forward required permission from chemistry, energy, and time. Earth was not generous, it was selective. The first billion years were not a march toward complexity. They were a test of endurance, a proving ground where only the most resilient systems survived long enough to matter. And so the planet continued, carrying its quiet biosphere forward through deep time, neither rushing nor retreating, refining itself through patience rather than force, and preparing unknowingly for transitions that would one day reshape the surface of the world. As Earth carried on through this immense stretch of deep time, one of the most striking truths about the planet was how completely unwitnessed its transformation remained, unfolding without eyes to observe it, without memory to record it, and without any awareness that something extraordinary was taking place at all. The planet did not know it was becoming habitable. Life did not know it was preparing for complexity. Everything simply persisted, step by step, cycle by cycle, bound by the quiet logic of survival rather than by any sense of destiny. The biosphere, still composed almost entirely of microscopic life, existed in a state of near-permanent humility, constrained by chemistry, moderated by energy, and shaped by a planet that offered neither comfort nor cruelty, only conditions that either allowed persistence or quietly removed it. Nothing about this world rewarded ambition. It rewarded restraint. The organisms that endured were those that learned to exist on the edge of activity, capable of slowing themselves almost to stillness when resources waned, then resuming growth cautiously when conditions allowed, never pushing so far that collapse became inevitable. This rhythm of expansion and contraction became fundamental, woven into the deepest biological processes, shaping not just behavior but the very architecture of life itself. Within cells, systems evolved to sense the environment and respond proportionally, rather than reacting blindly, allowing life to conserve energy, protect its internal stability, and avoid irreversible damage during periods of stress. These systems were not sophisticated in any human sense. They were simple, robust, and effective, and they lasted. Earth's surface continued to change, but slowly enough that life could track those changes without being overwhelmed. As coastlines shifted, shallow seas opened and closed, and mineral-rich sediments flowed into the oceans, feeding biological processes that depended on steady, long-term nutrient supply rather than sudden abundance. The planet became predictable enough for adaptation, not safe, but knowable. In this world, life did not seek novelty, it refined reliability. Each successful lineage was one that had discovered how to operate within narrow margins without exceeding them, how to tolerate uncertainty without demanding stability, and how to recover from loss without requiring perfection. This refinement unfolded across spans of time so vast that change became almost philosophical rather than historical, challenging any attempt to assign beginnings or endings, because each transition blurred into the next, each improvement layered upon countless others that had already vanished without record. The oceans, still the primary habitat for life, acted as both sanctuary and constraint, buffering organisms from temperature extremes while simultaneously limiting access to light and energy, forcing life to balance efficiency against opportunity. Shallow waters offered sunlight but fluctuated more dramatically. Deep waters offered stability but limited energy. Life adapted to both. Between these extremes lay boundary zones, where gradients of light, chemistry, and temperature intersected, creating environments rich in possibility but also prone to instability, rewarding organisms that could exploit brief windows of opportunity without depending on their permanence. These zones became engines of diversity. As these systems matured, interactions between organisms grew increasingly indirect, mediated through changes to the environment rather than through direct competition, as metabolic byproducts altered local chemistry in ways that shaped which strategies could persist. Life influenced life without contact. Evolution became ecological. This indirect interaction produced a biosphere that functioned less like a battlefield and more like a shifting network of constraints, where success depended not on eliminating others, but on fitting into the evolving structure of the system as a whole. Balance mattered more than dominance. The planet's long cooling trend continued, reducing the frequency of catastrophic resurfacing events and allowing surface environments to persist longer, though never permanently, reinforcing life's reliance on adaptability rather than attachment to place. Habitats came and went, lineages followed or retreated, nothing was fixed. As stability increased, so did the capacity for biological memory, not in the sense of consciousness, but through genetic continuity that allowed successful adaptations to persist long enough to shape future evolution. Information accumulated, complexity deepened. Still, complexity remained internal. Life grew more sophisticated without becoming larger. Structures became more organized without becoming visible. Systems layered upon systems, hidden beneath water and stone. This invisibility shaped the pace of change. Without the feedback of large-scale disruption, evolution proceeded cautiously, testing new arrangements incrementally rather than risking radical transformations that could fail catastrophically. Innovation was conservative, yet even conservative innovation accumulates power over time. Each refinement reduced vulnerability. Each improvement expanded possibility. Life was slowly constructing the foundation upon which future expansions would rest. The atmosphere continued its gradual transformation, with oxygen levels oscillating but trending upward over long spans, altering chemical pathways and energy availability in ways that favored organisms capable of managing oxidative stress. This shift did not produce immediate abundance. It imposed discipline. Life adapted by developing systems to neutralize damage, repair internal structures, and regulate chemical reactions with increasing precision, further reinforcing resilience at the cost of speed. This trade-off would define the future of complexity. The sun, too, continued its slow evolution, brightening imperceptibly over millions of years, increasing the energy reaching Earth's surface and subtly expanding the range of conditions under which life could persist. Life adjusted, not abruptly. Gradually through all of this, the planet remained quiet. No explosions of diversity, no visible transformations, just persistence. It is tempting to view this era as waiting, but waiting implies anticipation. Earth and life anticipated nothing, they simply continued, and in that continuation something essential was forged, a biosphere capable of surviving uncertainty, a planet capable of supporting continuity, a partnership that no longer collapsed at the first sign of change. The first billion years were not a prelude to drama. They were a filter, a long, unforgiving test that stripped away everything that could not endure. What remained was subtle, patient, and extraordinarily resilient. Every later transformation would depend on this foundation. Every future expansion would draw from the systems refined here. Without this deep silence, nothing else could follow. And so Earth turned on beneath a slowly brightening sun, carrying life forward through deep time, refining it not through spectacle but through endurance, shaping a world where change became possible precisely because it was no longer constant. We remain within this stillness, not moving toward an ending, not announcing a beginning, but continuing through the long stretch where Earth learned how to hold life without destroying it, and life learned how to exist without demanding more than the planet could give. After more than 1 billion years of patience, endurance, and quiet transformation, Earth arrived at a moment that cannot be marked by a single date, a single place, or a single event. There was no sudden shift, no clear dividing line, no instant when the planet became what it is today. Instead, there was continuity. The Earth that emerged from this deep silence was not gentle, but it was stable enough, not welcoming, but permissive. Not alive in the way we recognize now, but irrevocably changed by the presence of life that had learned how to persist without overwhelming the world that sustained it. The surface of the planet still looked empty, oceans still dominated, land still lay bare beneath an unfamiliar sky. Yet beneath that surface, Earth had crossed a threshold that could never be uncrossed. Life was no longer an experiment, it was a feature. The systems that had formed during the first billion years, chemical cycles, microbial networks, regulated cells, resilient metabolisms, had become self-sustaining. They no longer depended on rare conditions or fragile coincidences. They endured because they fit the planet. Earth had learned how to hold life. Life had learned how to live within Earth, and neither would ever be the same again. Everything that followed, forests, animals, ecosystems, intelligence, would be built upon foundations laid during this quiet era, not through sudden innovation, but through accumulation. The oxygen we breathe began as a waste product. The stability of our climate began as microbial chemistry. The complexity of our bodies began as internal regulation inside cells that lived for billions of years without being seen. The most important chapter in Earth's history did not announce itself. It unfolded slowly, patiently, and without witnesses. This is what makes the first billion years so profound, not that life appeared, but that it endured. In a universe shaped by violence, randomness, and impermanence, Earth became something rare, a planet that did not reset, a world that allowed continuity, a place where complexity could accumulate rather than vanish. Every breath you take is connected to this ancient silence. Every living thing traces its lineage back through this deep, quiet past. Not to a moment of creation, but to a long discipline of survival. Earth did not rush toward life. Life did not rush toward complexity. Together, they learned patience, and that patience changed everything. If you've made it all the way through this journey, through fire, silence, chemistry, endurance, and deep time, thank you for staying here and for giving this story the time it deserves. If you enjoy documentaries like this and you want more calm, long-form explorations of Earth, history, and deep time, make sure you subscribe to the channel so you don't miss what comes next. And if this story made you think even for a moment, I'd really love to hear from you. Leave a comment below and tell us what part of Earth's deep past you find most fascinating. Thank you for watching.